Welcome. Today we're getting into something really fascinating. How helicopters actually fly.
Right, the aerodynamics behind it all. It seems almost magical, but it boils down to some core physics principles.
Exactly. We're going to unpack those principles, looking at the forces involved, how lift is made, the different kinds of drag, and, the nitty-gritty of rotor blades and airflow.
We'll also look at how these things change depending on what the helicopter's doing, hovering, flying forward, even that critical maneuver, auto-rotation.
It's all about balance, isn't it? Understanding the forces and how pilots control them.
Precisely. That's the key. Pilots are constantly managing this balance through the controls.
So let's start with the basics. The four forces of flight. First up, weight. Simple enough.
Pretty much. It's just gravity pulling the helicopter down, acting on its total mass. Think about just one rotor blade. It might weigh 100 pounds. That alone gives you an idea.
And opposing that weight is lift, the upward force.
Yes, lift is the aerodynamic force generated by air moving over those rotor blades. And what's really interesting is how small a pressure difference you need.
How small?
Well, maybe just 1 pound per square foot difference between the top and bottom surface can be enough lift to counteract that 100-pound blade's weight. It's quite efficient.
Wow. Okay, so how does that tiny pressure difference happen? It's the shape of the blade, right? The airfoil.
Exactly. It's down to Bernoulli's principle. The air flowing over the curved top surface has to travel further, so it speeds up.
Faster air means lower pressure. I remember that.
That's it. Lower static pressure on top, higher static pressure below, and that difference pushes the blade up. That's your lift.
Got it. Faster air, lower pressure on top. Is Newton involved too? That whole equal and opposite reaction idea.
Absolutely. As the blades push air downwards, the downwash, there's an upward reaction force on the blades. That contributes to lift as well, though usually the pressure difference from Bernoulli is the bigger player.
Okay, so weight down, lift up. Then we need movement. That's thrust.
Correct. Thrust is the force from the rotor system that overcomes drag. And crucially, in a helicopter, thrust isn't just forward. It can be directed, well, pretty much anywhere forward, back, sideways, even straight up.
Giving it that amazing maneuverability. And finally, drag, the force holding it back.
Right. Drag is air resistance. It opposes thrust, always acting parallel to the relative wind, trying to slow the helicopter down.
So these four forces are in this constant tug of war. But you mentioned drag isn't just one simple thing.
No, not at all. We usually break total drag down into three main types. First, there's profile drag.
Profile drag. That sounds like the drag of the blades themselves.
That's right. It's the friction of the blades moving through the air. It has two parts. Form drag, which is caused by the shape of the blade creating turbulent air behind it, kind of like the weight behind a boat.
Okay.
And skin friction, which is literally the air dragging along the microscopic roughness of the blade's surface.
Even on a smooth-looking blade.
Yep, even then. So that's profile drag. Then you have induced drag.
Induced, like it's caused by something else.
Exactly. It's caused by producing lift. Remember the pressure difference. High pressure below wants to curl around the blade tip to the low pressure above. This creates swirling vortices.
Ah, those wingtip vortices you see on planes sometimes.
Similar idea, yes. These vortices effectively tilt the lift vector slightly backward, and that backward component is induced drag. It's actually most significant at lower air speeds when the blades need a higher angle of attack to generate lift.
Interesting. More lift needed at low speed means more induced drag. Okay, what's the third type?
Parasite drag. This is the drag from everything except the lifting surfaces. So the fuselage, landing gear, rotor mast, antennas, anything sticking out in the wind.
The non-aerodynamic bits, basically.
Pretty much. And unlike induced drag, parasite drag gets much, much worse as airspeed increases, squarely related to velocity, actually.
So they work in opposite ways. Induced drag high at low speeds, parasite drag high at high speeds.
You got it. And if you plot total drag versus airspeed, you get this curve. There's a sweet spot, a speed where total drag is at its minimum.
And that's important.
Very. That minimum drag speed corresponds to LD max, the best lift-to-drag ratio. Flying near LD max gives you the best endurance or range, maximum efficiency.
Makes sense. Okay, we keep talking about the blades generating lift. Let's focus on that airfoil shape. That's the heart of it all.
Absolutely. An airfoil is specifically designed to generate way more lift than drag when air flows over it correctly. Rotor blades are airfoils, but so are things like stabilizers on the tail boom.
So what defines an airfoil shape? What are the key parts?
Okay, picture a cross-section. You've got the leading edge, the front part that meets the air first, then the trailing edge, the sharp back edge.
Leading and trailing edge. Got it.
A straight line connecting them is the chord line. The length of that line is the chord. Then there's the mean camber line. That's a line drawn halfway between the upper and lower surfaces. The curvature of this line, the camber, is really important.
Right, that curve is what makes the air speed up on top.
Exactly. Now, how the air hits that airfoil is critical. The direction the airfoil is moving determines the relative wind the airflow the blade experiences, always opposite to its motion.
But for a spinning rotor blade, that motion is complex, right? It's spinning and the helicopter might be moving.
Correct. The flight path velocity is that combination. But there's another factor, induced flow. That's the air being pulled downwards through the rotor disc by the blades themselves.
The downwash?
Right. So the actual wind the blade feels isn't just the horizontal relative wind from rotation and movement. It's that relative wind combined with the downward induced flow. We call this the resultant relative wind.
Resultant relative wind, okay.
Yeah.
And that's what determines the angle of attack.
Precisely. The angle of attack, or AOA, is the angle between that resultant relative wind and the chord line. This is what dictates how much lift and drag are produced.
And that's different from the angle the pilot sets.
Yes. The angle the pilot controls directly with the collective and cyclic is the angle of incidence, or blade pitch. That's the angle between the chord line and the plane of the rotor hub. So the pilot sets the pitch, which influences the AOA based on the resultant relative wind.
So pitch is the input, AOA is the aerodynamic result.
Got it. Now some blades look symmetrical, top and bottom. Others are clearly curved on top. Why the difference?
Good observation. Those are symmetrical versus non-symmetrical, or cambered, airfoils. A symmetrical one has identical top and bottom surfaces. It produces zero lift at zero AOA. Many light helicopters use them, partly for simpler mechanics.
And the non-symmetrical ones?
They have that camber, the curved upper surface. They can actually produce lift even at zero or slightly negative AOA. They generally offer better lift-to-drag ratios, but can introduce other complexities, like twisting forces or torque.
Makes sense. And I've noticed blades aren't flat along their length either. They seem twisted.
Yes, that's blade twist. It's a crucial design feature. The angle of incidence is higher at the root, near the hub, and gradually decreases towards the tip. Why do that?
Because the blade tip travels much faster than the root. Twisting the blade helps distribute the lift more evenly along the span. If it wasn't twisted, the tips would generate vastly more lift than the roots, putting huge stress on the blade root. Twist balances things out.
Clever. Ensures the whole blade is working efficiently. So, just to recap the blade parts. Hub in the center, root where it attaches, tip at the end, and that twist along the length.
You got it. Hub, root, tip, twist.
Okay, let's dive back into the airflow around that spinning rotor disc. We mentioned relative wind and induced flow.
Right, so the rotational relative wind is purely from the blade spinning. It's fastest at the tips, zero at the hub, and always perpendicular to the blade's leading edge, in the plane of rotation.
But then you add the helicopter's movement.
Exactly. Forward flight adds a component, backward flight adds one sideways, that modifies the horizontal part of the relative wind.
And then there's the vertical part.
Yes, mainly that induced flow, the downwash. It's strongest in a hover when the rotor's pulling stationary air down. Climbing or descending also adds a vertical component to the air relative to the blades.
And it's the combination, the resultant relative wind, that matters for AOA.
Correct. The induced flow always points downwards, so it reduces the angle of attack compared to what it would be with only the horizontal relative wind.
Now, you hear pilots talk about ground effect. What's that about? Does the ground change the airflow?
It absolutely does. When a helicopter hovers close to the ground, usually within one rotor diameter, the ground interferes with the downwash. It can't escape outwards as easily.
So it kind of dams up the air.
In a way, yes. This restriction reduces the induced flow velocity. Less downward flow means the resultant relative wind becomes more horizontal, closer to the blade's plane of rotation.
Which means less power needed.
Exactly. The lift vector becomes more vertical, induced drag decreases, and the rotor system becomes more efficient. It takes noticeably less power to hover in ground effect, IGE, than out of ground effect, OGE.
So climbing away from the ground, you leave that cushion behind.
Right. Out of ground effect, the induced flow increases again. To maintain the same lift, the pilot has to increase the blade pitch, angle of incidence, which increases the angle of attack, but also increases drag. So more power is required for OGE hover.
Fascinating effect. Okay, let's clarify angle of incidence and angle of attack one more time. Pilot controls incidence.
Pilot controls angle of incidence pitched directly with the collective and cyclic. That's the mechanical angle of the blade relative to the hub.
And angle of attack is?
Angle of attack is the angle the blade aerodynamically experiences. It's between the chord line and the resultant relative wind, the actual airflow hitting the blade, including induced flow. So pilot changes pitch, which affects AOA, which determines lift and drag.
And you can only increase that AOA so much, right, before something bad happens.
Correct. Increase AOA, lift increases.
Mm-hmm.
Up to a point. That's the critical angle of attack. Go beyond that, and the airflow separates from the top surface of the airfoil. It becomes turbulent.
Stall.
Exactly. Lift plummets, drag shoots up.
Yeah.
Definitely want to avoid stalling the rotor blades.
Okay, let's put all this together. How does it apply to actual flying? Starting with hovering, you said that's the hardest.
Arguably, yes. Because the helicopter is generating all its own disturbed air, its own downwash. The pilot is constantly making tiny corrections, cyclic for drift,
Collective for altitude.
throttle for RPM, and pedals for heading to counteract that main rotor torque.
It's a real balancing act.
Yeah.
And there's that translating tendency, too. The helicopter wants to drift sideways.
Yes, the tail rotor pushes sideways to stop the fuselage from spinning, but that sideways push also shoves the whole helicopter in that direction.
How do they deal with that?
Designers compensate in various ways, tilting the transmission slightly, rigging the controls so the pilot naturally holds input against it, or sometimes the fuselage just hangs slightly tilted in a hover. In forward flight, it means the helicopter naturally flies slightly crabbed into the wind.
Clever solutions. What about the fuselage swinging underneath, like a pendulum?
That's pendular action. Because the weight hangs below the rotor hub, abrupt control inputs can make it swing. Smoothness is key for stability. Also, related to stability is coning.
Coning.
Yeah.
The blades flexing upwards.
Right. Lift pulls them up. Centrifugal force pulls them out. They find a balance, forming a shallow cone shape. But if rotor RPM gets too low, centrifugal force decreases and the blades cone upwards excessively. That's dangerous.
Okay, hover requires constant vigilance. Vertical flight, just straight up or down.
Relatively simpler.
Yeah.
Aerodynamically. Increase collective pitch, increase lift, you go up. Decrease pitch, decrease lift, you go down. Assuming constant RPM and no wind, of course.
All right. Now forward flight. The forces are balanced, but how do you get moving?
The pilot uses the cyclic control to tilt the entire rotor disc forward. This tilts the total lift thrust vector forward, providing a horizontal component to overcome drag and accelerate the helicopter.
Does that affect lift initially?
Yes. Tilting the lift vector forward reduces the purely vertical component slightly, so you might get a momentary sink as you transition. But then something beneficial happens. Translational lift.
Translational lift, is that like ground effect? Makes things more efficient.
It does improve efficiency, but it's different from ground effect. As the helicopter moves forward, the rotor disc starts flying into cleaner, less disturbed air, instead of just recirculating its own downwash.
Oh, so it's getting fresh air to work with.
Exactly. This smoother inflow increases rotor efficiency. As speed builds, usually around 16 to 24 knots, the rotor completely outruns its own turbulent wake. This point is called effective translational lift, or ETL.
And you can feel that.
Often, yes. You might notice a shudder or vibration as you pass through it, sometimes called the transverse flow effect, just before ETL. The helicopter feels more responsive, needs less power to maintain altitude.
So moving forward actually helps the rotor work better. But doesn't forward flight create an imbalance? One side of the rotor moving faster than the other?
It does. That's called dissymmetry of lift. The blade advancing into the direction of flight experiences a higher relative wind speed, rotational speed plus helicopter speed. The retreating blade on the other side experiences a lower relative wind speed, rotational speed minus helicopter speed.
Higher speed means more lift. So the advancing side should lift more. Shouldn't that make the helicopter roll?
It would, except for blade flapping. Most helicopter rotors allow the blades to flap up and down on hinges.
How does that help?
The advancing blade, with its higher lift, naturally flaps upwards. This upward movement reduces its angle of attack, decreasing its lift. The retreating blade, with lower lift, flaps downwards. This increases its angle of attack, increasing its lift.
Ah, so flapping automatically balances the lift across the disc? That's ingenious.
It really is. It keeps the helicopter stable in forward flight. However, there's a limit. At very high forward speeds, the retreating blade has very low relative wind speed and needs a very high angle of attack to produce lift. It could eventually stall.
Retreating blade stall. A speed limit for helicopters.
Pretty much. Pilots also use cyclic feathering, constantly adjusting the pitch of each blade as it goes around to help tilt the disc and manage lift distribution, including compensating for blowback, which is the tendency for the nose to pitch up in forward flight.
Complex stuff happening constantly. What about flying sideways or backwards?
Sideward flight means tilting the rotor disc sideways with the cyclic. It's less stable than forward flight, mainly because the fuselage creates a lot of drag from the side, and there's usually no vertical fin helping stability in that direction. Careful coordination of cyclic, collective, and pedals is needed.
And backwards.
Tilting the disc rearward also requires care, especially watching out for the tail hitting things, given the typical stabilizer position and skid design. Slower speeds are generally advisable for both sideward and rearward flight.
Sounds like they demand extra caution. Finally, turning. How does a helicopter bank and turn?
Very much like an airplane, in principle.
Yeah.
The pilot uses the cyclic to bank the helicopter, tilting the rotor disc sideways.
So the lift vector tilts?
Yes. The total lift force now has two components: a vertical component that still opposes weight, and a horizontal component that acts towards the center of the turn, the centripetal force that makes the turn happen.
But if some lift is now horizontal, doesn't the vertical lift decrease?
It does. So to maintain altitude in a turn, the pilot needs to increase the collective pitch, increasing the total lift generated by the rotor. The steeper the bank, the more collective pitch is needed.
Increase power to stay level in a turn. Makes sense. Okay, one last crucial area, auto-rotation. What happens when the engine quits?
Auto-rotation is the ability of the helicopter to descend and land safely without engine power. A freewheeling unit disengages the engine from the rotor, allowing the rotor to spin freely.
But what keeps it spinning?
The upward flow of air through the rotor disc as the helicopter descends. It's like a windmill effect.
Okay.
The air pushes the blades around.
How does that generate lift?
Aerodynamically, it's complex. During a vertical descent in autorotation, different parts of the blade do different things. Near the tip, the airflow actually pushes down on the blade, the driven region. Near the root, the angle of attack is very high, and it's stalled, the stall region.
So where does the driving force come from?
From the middle section of the blade, the driving region. Here, the angle of attack and the upward airflow combine to create a resultant aerodynamic force that's tilted slightly forward of the axis of rotation. This forward component keeps the blades turning.
So the descent itself powers the rotor, which generates enough lift for a controlled landing. Amazing.
It truly is. It relies entirely on these aerodynamic principles working together, allowing the pilot to manage the descent and flare for landing.
Well, that covers an incredible amount of ground. From the four basic forces to the complex interactions and maneuvers like forward flight and auto-rotation, it really gives you an appreciation for how these machines work.
Absolutely. Understanding these fundamentals really unlocks why helicopters can do what they do, and also highlights the challenges involved in flying them.
So, as you think about all this, maybe consider how designers make choices based on these principles. Why a certain number of blades? Why a specific airfoil shape? How might they optimize a design for, say, high speed versus heavy lift, purely based on tweaking these aerodynamic factors?
That's a great takeaway. Those design choices are deeply rooted in everything we've just discussed. It's a constant evolution based on understanding and manipulating these aerodynamic forces.
It certainly gives you a lot to think about. Thanks for joining us for this exploration of helicopter aerodynamics. We'll catch you next time.